Back. Now I'm going to illustrate something known as a thermoelectric converter. It's basically a simple device, right? And you just put it in two different baths, two different reservoirs of different temperatures, right? This one is a hot reservoir, this one is a cold reservoir. And by using the temperature difference between the two cold reservoirs, we produce electricity, and it converts that heat difference into electricity, and it runs this turbine. So I'm just going to dip it here into this. Okay, so you can see here how I am utilizing the temperature difference of the two reservoirs to run an engine. This is the basic essence of all heat engines, right? You're using the temperature difference, and then in physics we learned that the efficiency of the engine, the most efficient that it can be, is the Carnot efficiency, which is given by 1 minus the T cold over the T hot. Right? The bigger the difference of the two temperatures, the more efficient this is. So this is T hot minus T cold over T hot, right? It's the difference of the two temperatures, delta T over T hot, right? So if we can model this as a Carnot engine and we can measure the temperatures of the two baths, it's pretty much close to 0 Celsius, so 0.1 Celsius. So I have a bunch of ice in there. So my T cold is 0.1 Celsius. Right? And then I can put it in the hot bath. The hot bath is 71.4 Celsius. 71.4 Celsius. Right? So all I have to do is take the difference here. I can calculate the absolute maximum efficiency that this engine can be. Okay? The efficiency, we call that the Carnot efficiency. So the difference of the two temperatures, I don't have to change it to Kelvin. I can keep it in Celsius and just subtract them, because a difference in temperatures in Celsius is the same as the difference in the same temperatures in Kelvin. By subtracting that, I get 71.3. Then I divide it by the temperature of the hot reservoir in Kelvin. Now I have to convert it to Kelvin. So the temperature of the hot reservoir, 71.4. Then I add 273.15. And that's the conversion between Celsius to Kelvin, right? So then I'm going to get here, right? Later on, I'll show you what will happen if the two temperatures are very close to each other. I will dump out the cold water out, and I'll dump the hot water out. I'll put the two reservoirs that are about the same temperature. The efficiency will go way down, and it might even be 0, right? If the two temperatures are the same, then you can't even run an engine that way, okay? We come to the thermoelectric converter, and we put it in the two water baths. We measure the temperatures of the two water baths. This one, 29.8, and then this one, 32.1. So pretty close to each other, but you can see that the engine is not running. Even if I kind of get it going, the two temperatures are very similar. So right now, one of them is a little bit warmer than the other one. This one you can see here. The left one is 29.4 Celsius, right? Right now it's dropping to 29.3. The other one is 31.4. 29.3 over 31.4. Okay, so what's the maximum efficiency that it can have? Remember when we had one hot, one cold, we said the efficiency was, I believe, around 20%. Right now it is so inefficient, there is not much temperature difference, 0.6% efficient. In other words, it's so inefficient that it can't even get the wheel running. And that's even the most efficient that it can be. Engines are always less than the Carnot efficiency, so they're always going to be less than the maximum efficiency that is possible for them, right? So you can see that nothing is running right here. The other thing that I can do now is to run this experiment backwards. I can put in energy, right? I can take my power supply, put in energy as thermoelectric converter, delta T to E, E to delta T. In other words, I can use a temperature difference between the two, a temperature gradient, in order to cause electricity, in order to turn the turbine, right? Or I can put it on the choice B. I can have a power supply coming in here creating electricity. In other words, I'm putting in electricity, and then the two metals are going to change the temperature. In other words, they're going to reach different temperatures. One is going to be colder, one is going to be hotter. So in other words, I'm putting in energy, electrical energy, and then I'm producing difference of temperature of the two plates. And if I insert it in the water, the two waters are going to reach different temperatures, right? So I'm going to put this in like this. Actually, I decided to get two small beakers of water because their temperature can warm up quicker, so it'll be more noticeable. Let's check their initial temperature first. The left one says 27.9, 28.1 Celsius. They should be about the same temperature because I filled them up. 27.0, 27.6. So right now there's a little bit of temperature difference between the two. Okay, you can see here, I waited about 2 minutes now. The beaker on the right, okay, so my thermometer on the right, the beaker on the right, the water is about 29.3 Celsius. And then the beaker on the left, the water is 27.9 Celsius. Remember, that was already the warmer one. So now it's getting actually colder. So what happens, by putting in electricity, we're creating a temperature gradient between the two metals. The one on the left metal is getting colder, and the right metal is getting warmer. And the water is also, this one is going to get warmer, this one is going to get colder, but the water temperature is not that noticeably changing because water has a high specific heat. So let's see what it is now. By stirring it, you can kind of, okay, the water is still holding at 20, now it's 29.4, and then the one on the left, 27.7. Now if I actually touch the metals themselves, lift this up, this metal right here, the metal itself will warm up a lot. 45 Celsius, really warm. And if I put my finger on it, you actually burn on the one on the right. So you can see here, 40 Celsius. Now the one on the left, if I touch the metal, it's all the way down to 29, 28, even less, it's going down. 27.2. If we wait longer, this one will actually get cooler and cooler. 26.3, 26.2, 26, 25, and then so on and so forth. So the longer we wait, the one on the left is going to get cooler and cooler. The one on the right is going to get warmer and warmer. Okay? So you can see here how the thermoelectric converter was a good illustration of the heat engine. First, by creating a temperature gradient between the two hot and cold water, I was able to run the engine. Then I ran it backward as a heat pump, right? Heat pump, that means I used it as a way to create a temperature gradient. I put in electrical energy, and then the two metals became different temperatures, and then I was able to create a temperature difference between the two waters. One water went cold and one water went hot. This is how a heat pump works, and then the heat pump can either be used as a heater to heat your home, or as a refrigerator to cool down the contents of the refrigerator, right? So in other words, if this was the cold refrigerator and I want to cool it more, right? I want to cool the contents of the refrigerator more, it keep getting cooler, 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 but then I have to dump the heat to the other side. The other one is the back of the refrigerator, where the refrigerator dumps the heat. So I'm not really interested in dumping the heat to the back. That's not my interest. I want to cool the contents of the refrigerator. Or if I use this as a heater, what I will do is I will put, the heater is kind of the opposite of a refrigerator. I will take out on a cold winter day, I will take out heat from the outside, right? So I'm not really interested in how much heat I am taking from the outside, and then I will dump it to the inside. This beaker will be like the inside. So on a cold winter day, you're dumping the heat from the outside, which there is really no heat, right? It's already cold. You're making the cold colder, and then you're dumping that heat to the inside of the house. So this one will become a heater, and the inside of the house will keep getting warmer and warmer, right? So both of these illustrations, it can either be run as a refrigerator or as a heater. It's just the difference between the two is what the purpose of the refrigerator and the purpose of the heater is, okay? So this is a good illustration, and it also shows you when the temperature difference between the two is almost zero, then the efficiency of the engine is zero, and therefore you can't run a heat engine from that, okay? Thank you very much.